In the last lecture, we learned how to find the maximum and minimum value of functions. But in the real world, we're usually more interested in finding the maximum and minimum values given some constraint. As an example, you might be looking for the shape with the smallest surface area. That's not a really very interesting question. A more interesting question is, what's the shape with the smallest surface area given that its volume is blah? Another example might be, find the highest point on a mountain. That's not particularly interesting, it's just the top of the mountain. Slightly more interesting question is, find the highest point along the road that goes through the mountains. So how do we address questions like this, questions with a constraint? Well, what we're going to see in this lecture is that we can use the method of Lagrange multipliers to easily incorporate constraints into the maximum, minimum, extreme value problems. So let's see what the problem looks like from a geometric perspective. The first thing we have is the function that we're trying to find the maximum or minimum value of. We're going to call that z equals to f of x and y. We can visualize that as a surface in 3 dimensions. So again, what we would have done before, if we were looking for the maximum or min value, was just to look for where this point is highest or lowest, to look for its stationary points. However, this time we're going to have a constraint, and we're going to express that constraint in the following way. We're going to express it as an equation. The equation is going to be given by g of x and y is equal to 0. Now that's an expression relating x and y. In other words, it's a line in xy space. I can express that in terms of a curve. And every point on that curve satisfies my equation. So again, I've got my 2 ingredients. I've got my surface, z is equal to f of x and y, and I've got my constraint, which is an equation, g of x and y equals to 0. Now, how do I impose the constraint on my surface? Well, remember, there's no z dependence in that equation, g of x and y equals to 0, which means it's true for all values of z. So I can extend this infinitely in the z direction. And you can see that this shape is now going to intercept with our surface f of x and y. It's going to form some sort of curve on that surface. It might be slightly deformed because the surface itself is not flat. But you see it's going to form a curve on that surface. Now, our problem of finding the maximum or minimum values given the constraint g of x and y equals to 0 basically involves trying to find the point along this curve where f of x and y is max or minimum. So the way that we're going to address this problem mathematically is by introducing a new function that we're going to find extreme values for. This function is known as the Lagrangian, and it's going to combine our original function, f of x and y, and our constraint, g of x and y. So here's what we're going to do. We're going to form a new function, L. It's going to be made up of f of x and y and I'm going to subtract from that lambda times g of x and y. So again, f of x and y is our objective function. It's our function that we're looking for the maximum and minimum values of. And g of x and y is our constraint. So what is this new thing, lambda? Well, this is known as the Lagrange multiplier. It basically enforces my constraint. It's going to be an unknown value until I solve my equation. But the main point here is that all I've done is I've replaced my function f of x and y with a new function L of x and y and lambda. So now instead of having an extreme value problem for a function of 2 variables, I instead have an extreme value problem for a function of 3 variables. So I proceed in exactly the same way that I would have for functions of 2 variables. I take the derivative with respect to each variable and I set it equals to 0. So bearing in mind again that L of x and y is given by f minus lambda g, then the derivative of L with respect to x being equals to 0 gives me, first of all, the derivative of f with respect to x minus, well, lambda is just a constant, derivative of g with respect to x. df dx minus lambda dg dx. That's equals to 0, and so that gives me an expression relating the partial derivative of f with respect to x, the partial derivative of g with respect to x, and the Lagrange multiplier lambda. I can do exactly the same thing for the partial derivative with respect to y. Again, I'm looking for the stationary point of my new function L with respect to y, set the derivative equals to 0, and I end up with an equation relating the partial derivative of f with respect to y, partial derivative of g with respect to y, and my unknown Lagrange multiplier lambda. The last step is to take the derivative of L with respect to lambda. Remember, L is a function of x, y, and lambda. So lambda is an unknown, and so to fix that, I'm going to take the derivative of L with respect to lambda and set that equals to 0. But the trick here is that lambda only appears once in this equation. It only appears multiplying in front of this g of x and y. So what happens when I take the derivative of this function with respect to lambda? Well, this doesn't depend upon lambda, this doesn't depend upon lambda, so the only term that depends upon lambda is minus lambda times g. I take the derivative with respect to lambda of that and I get minus g. Setting that equals to 0 just gives me g of x and y equals to 0. The g of x and y equals to 0 was exactly our constraint. Remember that g of x and y equals to 0 basically told us how we had to constrain x and y when we were looking for the extreme value of f of x and y. So you see that I've ended up with 3 equations here. One equation relating the partial derivatives with respect to x, one equation relating the partial derivatives with respect to y, and I've gotten back my constraint as well. So this is 3 equations for 3 unknowns, x, y, and lambda. And we're going to have to solve those 3 equations simultaneously to find the solutions. Now what we're going to see is that in solving these solutions for x, y, and lambda, we have to be very careful that we actually capture all of the possible solutions. So we need to be sure that we're not dividing by anything that could be 0. Let's illustrate this with an example. So in this problem, we've got a function f of x and y equals to 12 plus 3x plus 4y. Now that's equation for a plane. So if you think about it, asking what the extreme value of that is doesn't make any sense. It extends to infinity. So the maximum value is plus infinity and the minimum value is minus infinity. So in this case, we actually need a constraint to make the problem make any sense. The constraint in this case is x squared plus y squared minus 1 equals to 0. That is, it's an equation for x and y equals to 0. Now notice that this is really just x squared plus y squared equals to 1. It's the equation for the unit circle. But I've rewritten it so that I've got everything on one side and then equals to 0. So I've rewritten it so that it looks like a constraint. G of x and y equals to x squared plus y squared minus 1 equals to 0. Now that always can be done, right? We can always take some expression involving x and y and rearrange it so that I get 0 on one side. And that's going to give me my g of x and y. So, Thinking about this problem geometrically, we can see that we have a plane in 3 dimensions. This is the objective function, the function that we're looking for the maximum or minimum value of. And we've got our constraint, which is the unit circle. Of course, the unit circle doesn't involve z, so I can extend this infinitely in the z direction to make a cylinder, and then ask for the intersection of that cylinder and the plane. So that's going to be this circle angled along the plane. The question then becomes, what's the maximum and minimum values of that plane, of that function on that circle? So we can also visualize that from above. I've colored here the plane so that blue is the lowest point on the plane and red is the highest point on the plane. And the purple or pink line here indicates, looking down, what this cylinder would look like. So you can see that the 2 points here, the pink points, indicate the highest and lowest points on this circle on the plane. Another way to think about all this is to think about you're driving on a road on this surface, on this sort of mountaintop or this mountainside. It's angled, and we're asking, where is the highest point on the road and where is the lowest point on the road? Okay, so let's set up the problem mathematically. We need to form this function L of x and y and lambda. So this is going to be given by combining the function we want to find the maximum or minimum value of, f of x and y, and subtracting from that lambda times g of x and y. In this case, f of x and y is 12 plus 3x plus 4y minus lambda times, and g is x squared plus y squared minus 1. So this is our function L of x and y and lambda. It's a function of 3 variables. I'm going to look for the extreme values of this 3-variable function by taking the partial derivatives. The partial derivative of this with respect to x, L subscript x, is going to be 3 minus lambda times the partial derivative of x squared, that's 2x. That's going to be 2 lambda x. And I'm going to set that equals to 0. Again, I'm looking for the stationary points. The partial derivative with respect to y will be 4 minus 2 lambda y equals to 0. And the last expression is going to be given by L subscript lambda, so the partial derivative of L with respect to lambda is equal to, well, you notice that my objective function, or my function L, only involves lambda here, so when I take the partial derivative, I'm going to get minus times x squared plus y squared minus 1, and that's all equals to 0. So these are my 3 equations for 3 unknowns. I'm going to solve these for x, y, and lambda. We can start off with the first equation, the partial derivative with respect to x, and solve this for x in terms of lambda. X is equal to 3 divided by 2 lambda. Now you might ask yourself, how can I divide by lambda here? Isn't it possible that lambda is equal to 0? And in fact, the answer to that is no. Lambda is not equals to 0. It cannot be equals to 0. And the reason for that, you can see it by looking back at our Lagrangian function, L of x and y and lambda. So you see that if I set lambda is equal to 0 in this expression, what happens is that L of x and y is equal to f of x and y. That's our original function, f of x and y. So in other words, setting lambda is equal to 0 means that the extreme problem that I'm trying to solve is really trying to find the extreme values of f of x and y. It's looking for the global maximum and minimum values. There's no constraint. And of course, that doesn't make any sense in this problem. So you see that setting lambda is equal to 0 turns off our constraint. So that for that reason, we can never have lambda equals to 0 in these problems. Looking again at the partial derivative of L with respect to y. We can also solve this for y in terms of lambda. I'm going to get 4 over 2y. Again, lambda can be equals to 0. And the partial derivative of L with respect to lambda, well, that's just going to give me back my constraint again. I'm going to write that x squared plus y squared equals to 1. It's the unit circle. So here are my three equations for three unknowns. X is equal to 3 over 2 lambda, y is equal to 4 over 2 lambda, and x squared plus y squared equals to 1. Let's substitute those expressions for x and y in terms of lambda into my constraint to get a single expression for lambda. So x was equal to 3 over 2 lambda, y was equal to 4 over 2 lambda is equal to 1. 3 over 2 lambda squared is 9 over 4 lambda squared plus 16 over 4 lambda squared. Adding those together is 25 over 4 lambda squared, and that's equals to 1. So that implies that lambda squared is equal to 25 over 4, which in turn implies that lambda is equal to plus or minus 5 over 2. So we've solved the expression lambda squared equals to 25 over 4 by taking the square root, and of course we pick up a plus or minus. So you see that we get two different possible solutions here, and those are going to correspond to two different possible values of x and y. To figure out what those values are, we now need to substitute back into our expressions for x and y given here. So let's start off with lambda is equal to plus 5 over 2. In that case, x is equal to 3 over 2 lambda, so that's going to be 3 over 5. And y is equal to 4 over 2 lambda, so that's going to be 4 over 5. So we get the point x is equal to 3 over 5, y is equal to 4 over 5. We can do the same thing for lambda is equal to minus 5 over 2. So again, x is equal to 3 over 2 lambda, which gives me minus 3 over 5. Y is equal to 4 over 2 lambda, which gives me minus 4 over 5. So we get the point minus 3 over 5 minus 4 over 5. Those are our 2 points. Now, how do we know which one's the maximum and which one's the minimum? Well, this is where the process of the method of Lagrange multipliers differs from what we saw in the last lecture. In this case, we're not going to use the second derivative test to find the maximum and minimum values. We're going to simply substitute these points, these values of x and y that we found, back into our original function and simply see which one is the maximum and which one is the minimum. So again, the difference between the method of Lagrange multipliers and the method of finding the extreme values is that we do not use the second derivative test here. We simply substitute the points into our original function. So our function was f of x and y is equal to 12 plus 3x plus 4y. So let's find out what those values are at the point 3 over 5, 4 over 5. So that's going to be 12 plus 9 over 5 plus 16 over 5. That's going to be 12 plus 25 over 5. Which is 12 plus 5, which is equal to 17. So that's the value of our function at the point 3 over 5, 4 over 5. Let's do the same thing for the value at minus 3 over 5, minus 4 over 5. So we've got 12 minus 9 over 5 minus 16 over 5, which is equal to 12 minus 25 over 5, which is 12 minus 5, which is 7. So you can see that it's now obvious which of these points is the maximum and which is the minimum. The point 3 over 5, 4 over 5 has a value of 17, so that's the maximum. The point minus 3 over 5, minus 4 over 5 has a value 7, so that's the minimum. So our point x is equal to 3 over 5, y is equal to 4 over 5, and z is equal to 17 is a maximum. And our point minus 3 over 5, minus 4 over 5, 7 is a minimum. And those correspond exactly to the points that we saw in the figure. This point here and this point here. So again, the important thing to remember in these problems is that once we've found our points, we do not use the second derivative test to figure out if they're maximum or minimum. We just substitute them in. Let's look at another example. So in this problem, we've got a function x to the power of 4 plus y to the power of 4, and we're looking for the constraint x plus y minus 1 equals to 0. Once again, I've rewritten my constraint as everything involving x and y on the left-hand side equals to 0. So you can see that my constraint is simply g of x and y is equal to x plus y minus 1. So what does this problem look like geometrically? Well, the function x to the power of 4 plus y to the power of 4, you can see, is quite hollowed out. It's quite a concave function. It increases quite rapidly when you go away from 0. The constraint x plus y minus 1 is equal to 0, well, that's just a straight line. Y is equal to mx plus c. In the straight line, when I extend it in the z direction, is a plane, a vertical plane. So you can see that I'm looking for the maximum or minimum value of this function along this plane. And this is where we have to use a little bit of geometric reasoning to figure out whether or not my point that I'm going to find is a maximum or minimum value. Remember that the function is increasing infinitely as when I move away from the origin, but my constraint also extends infinitely in the xy plane. So I could go forever and ever and ever out here to get bigger and bigger and bigger values of my function, and ever and ever and ever out this direction to get bigger and bigger values of my function that way. So the point that I'm going to find has got to be a minimum. I'm not going to be able to tell that just by substituting in the values. I've got to figure it out by thinking about what this function is. So let's once again set up my Lagrangian function for this problem. So I've got L of x, y, and lambda is equal to f of x and y, so that's going to be x to the power of 4 plus y to the power of 4, minus lambda times my constraint, x plus y minus 1. This is my function. Notice that it's important here to correctly put in the function f of x and y first, minus lambda times g of x and y. That is, it's important to distinguish between the function that you're looking for the maximum and minimum values of, and the function that's constraining you. You don't want to get those two confused. So once again, we're going to take partial derivatives. The partial derivative of this function with respect to x is 4x cubed minus lambda. That's equals to 0. Again, lambda is not going to be equals to 0, and I can solve this right away for x. So this is going to be x is equal to lambda over 4 to the power of 1/3, the cube root of lambda over 4. Let's do the same with partial derivative of L with respect to y. That's going to be 4y cubed is equal to lambda. Oh, sorry. Minus lambda is equal to 0. Solving that, y is equal to lambda over 4 to the power of 1/3, the cube root. Then you might ask yourself here, why don't I have a plus or minus in front of those? Well, the plus or minus only applies to square roots or to even roots. For cube roots and fifth roots and seventh roots, we never have a plus or minus, because if you think about it, lambda over 4 times lambda over 4 times lambda over 4, y times y times y will have the same sign as y, right? So we never have a plus or minus. The last equation we have is L subscript lambda is equal to minus x plus y minus 1. That's equal to 0. And again, that's going to give me back my constraint. X plus y minus 1 equals to 0. So once again here I've got 3 equations for 3 unknowns, x, y, and lambda. Okay, so let's try and solve this. We're going to use the same trick again. We're going to substitute the first 2 expressions, x and y, in terms of lambda into this expression and try and solve for lambda. So we've got lambda over 4 to the power of 1/3 plus lambda over 4 to the power of 1/3 is equal to 1. So that gives me 2 times lambda over 4 to the power of 1/3, or if I write it like this, is equal to 1. Dividing by 2 on each side gives me lambda over 4 to the power of 1/3 is equal to 1/2. And to get rid of that power of 1/3, I'm going to have to cube both sides. So taking the third power of both sides gives me lambda over 4 is equal to 1 over 2 to the power of 3, which is 1 over 2 times 2 times 2 is 8. That's going to give me an expression for lambda. Lambda is equal to 4 over 8, which is 1/2. So one of the things you notice here is that we only get one value of lambda here. We only get lambda is equal to 1/2. So compare that with the last problem where I had lambda is equal to plus or minus 5 over 2. Here I've only got one value of lambda. And that's telling us that there's only one extreme value here. So let's substitute in and find out what that value is, x and y. So we've got lambda is equal to 1/2. We saw that x was equal to y was equal to lambda over 4 to the power of 1/3. Lambda is 1/2, so I get 1 over 8 to the power of 1/3. That's the cube root of 1 over 8, which is 1/2. So I get the point x is equal to 1/2, y is equal to 1/2. What's the value of my function there? Well, f of x and y was x to the power of 4 plus y to the power of 4. 1 over 2 to the power of 4 is 1 over 16. Let's move that downstairs. Equals to 1 over 16 plus 1 over 16. which is equal to 1/8. So our extreme point, x equals to 1/2, 1/2, y is equal to 1/2, z is equal to 1/8. And the question now is that a maximum or a minimum value? We can't tell just because it's just from comparing it to the other points, because there is no other points to compare it to. We only have one extreme value on this line. But again, thinking about it geometrically, the answer is obvious. If we look back at our figure, you can see that this thing has to be a minimum value. There is no maximum value. So this point is a maximum. Is a minimum. Okay, let's look at another example. Example 3. So in this case, we're looking for the dimensions of a closed circular cylinder of smallest area, whose volume is 16 pi cubic centimeters. So let's think about what this problem looks like. I'm looking for a cylinder. What's the surface area of a cylinder? Let's draw my cylinder. And let's say that its height is given by h. And let's say that its radius is given by r. Well, the caps at the top and the bottom are going to be have an area of just pi r squared. And there's one at the bottom as well. So I get 2 pi r squared as the contribution from the caps on this cylinder. And what about the circular part, the outer side? Well, we know that the height of it is h, and I know that the length of it, if I opened it up and unrolled it, would be given by the circumference of the circle with radius r, which is just 2 pi r. So if I unroll this thing, it would have dimensions h multiplied by 2 pi r. So the area from the sides is just 2 times pi times r times h. So the total surface area is 2 pi r squared plus 2 pi r h. What about the volume? Well, that's going to be given by the height times the cross-sectional area, so h times pi r squared, and that has to be equals to 16 pi. So you can see that my function that I'm trying to find the maximum or minimum value of is the surface area, 2 pi r squared plus 2 pi r h. And the constraint g of x, g of r, and h in this case is equal to pi r squared h minus 16 pi. So pi r squared h minus 16 pi. So once again, I've rearranged my constraint so that it's equal to 0. So if we set up our Lagrangian and take the partial derivatives, I'm going to end up with the partial derivative of this is equal to lambda times the partial derivative of this here. Partial derivative of s with respect to r is given by 4 pi r plus 2 pi h. That's equal to lambda times the partial derivative of this, so that's lambda 2 pi r h. And I can solve that for an expression for r, h, and lambda. Likewise, I can look for the partial derivative of s with respect to h and set that equals to lambda times the partial derivative of g with respect to h. That gives me an expression for lambda in terms of r. And notice here that, in fact, not only can lambda not be equals to r, lambda not be equals to 0, but also r can't be equals to 0. R cannot be equals to 0 because then I would just get a volume of 0. and that doesn't satisfy the constraint. My radius cannot be 0 because that gives me 0 volume, and I have a constraint on the volume. The final equation I have, of course, is just my constraint, and that gives me another equation for R and H. So I've got my three expressions for R, H, and lambda, and you can work through there what the values of those are when you substitute it all in. What you find is that R is equal to 2 and H is equal to 4. Those are the dimensions of the cylinder. Now the question again is, we've only got 1 point, so are we looking at here the maximum or the minimum surface area? Well, again, thinking about it geometrically, we can always make this thinner and thinner and thinner, and longer and longer and longer, so that it has more and more surface area, but a constant volume. So I can make it really, really long and thin and skinny, have a very large surface area because it's so long and skinny, but have a constant volume. So there is no maximum surface area. There's no maximum surface area. So what we're looking at here is the minimum surface area. The minimum surface area. And that's given by the values of R equals to 2 and H is equal to 4. Okay, let's look at another example, example 4. In this example, we're looking for the minimum distance between a plane and a point. So it's kind of hard to see from this exactly what the constraint would be and what the function is we're maximizing and minimizing. So we're going to have to think about this a little bit. So let's draw a little sketch of what we're doing here. I have my plane. I've got a point on that plane. Let's call it P. I don't know what exactly that point is on that plane. And I have a point 5, 7, 11. And I'm looking for essentially the values of x, y, and z that give me the smallest distance, d, of x and y and z between the point P and 5, 7, 11. So it seems that the function that I'm trying to find the maximum or minimum value of is the distance, and the constraint is that my point P has to be on this plane. My values of x, y, and z have to satisfy this expression here, which is the expression for all the points on the plane. Okay, so how do I specify my max-min problem? Well, I'm looking for the minimum value of the distance between these points. So P again is unknown x, y, and z. So the distance between 5, 7, 11 and x, y, and z is the square root of x minus 5 squared plus the y minus 7 squared plus z minus 11 squared. And my constraint is that x, y, and z have to lie on this expression on this plane. So in other words, x, y, and z have to satisfy this equation. So I can rearrange that so that g of x, y, and z is equal to 3x plus 4y plus 12z minus 6 is equal to 0. So that's all I need. I can set up my Lagrangian at this point, put in my Lagrange multiplier. I now have a function of x, y, z, and lambda, and look for the extreme values by taking the partial derivatives with respect to x, y, and lambda, and z, and solving. However, this is going to get pretty messy pretty quickly, because you see that I've got a square root here. Every time I take the derivative of this, it's going to involve the chain rule, and it's going to be pretty horrible. So in fact, there's a nice simplification that we can use, and it's because that the distance is going to be a minimum whenever whatever's inside this square root is also a minimum. So think about it. Instead of taking the distance between the 2 points as being our function that we're minimizing, let's take the distance squared as being the function that we're going to minimize. The great advantage of this is that I get rid of that square root. So instead of minimizing the square root of all this stuff, let's minimize x minus 5 squared plus y minus 7 squared plus z minus 11 squared, subject to the constraint 3x plus 4y plus 12z minus 6 is equal to 0. So again, the trick I'm using there is that this function here is just as good as this function here in terms of finding the minimum value. Alright, so now our problem is set up. I can form my Lagrangian L of x, y, z, and lambda is equal to x minus 5 squared plus y minus 7 squared plus z minus 11 squared. And I'm subtracting from that minus lambda g of x and y, so that's 3x plus 4y plus 12z minus 6. Start taking derivatives. Partial derivative with respect to x is going to be 2 times x minus 5 minus 3 lambda is equal to 0. Derivative with respect to y is going to be 2 times y minus 7 minus 4 lambda is equal to 0. Derivative with respect to z is going to be 2 times z minus 11 minus 12 lambda is equal to 0. And of course, the derivative with respect to lambda will give me minus 3x plus 4y plus 12z minus 6 is equal to 0. So these are my 4 equations for 4 unknowns. So let's rearrange these. I'm going to use the same technique I used before. I'm going to solve for x, y, and z in terms of lambda, substitute those expressions into my constraint to solve for lambda, and then find what x, y, and z are. So x will be equals to 5 plus 3 lambda divided by 2. Y will be 7 plus 4 lambda divided by 2. And z will be 11 plus 12 lambda divided by 2. Let's take those expressions now and substitute them into my constraint. So 3x, x is given by 5 plus 3 lambda over 2, plus 4 times y, y was 7 plus 4 lambda over 2, so we can cancel a factor of 2, plus 12 times z, 11 plus, again, 12 lambda over 2, so that's 6 lambda, minus 6 is equal to 0. So this is a single expression for lambda. I get, let's see, 15 plus 9 lambda over 2 plus 28 plus 8 lambda plus 12 times 11 is 121 plus 6 times 12 is 72 lambda minus 6 is equal to 0. And you can solve that expression. I'll let you do that yourself. What you're going to find is that lambda is equal to minus 2. That is the solution for that expression. And when you substitute in those values into expressions for x, y, and z, you're going to find that x is equal to 2, y is equal to 3, and z is equal to minus 1. So that is the point on the plane satisfying the constraint 3x plus 4y plus 12z minus 6 is equal to 0, that has the smallest distance. So again, the distance here, if I substitute in, and this time of course I have to use the square root of x minus 5 squared, x is equal to 2, y is equal to 3 minus 7 squared plus z minus 11 squared, so z is equal to minus 1. And what you'll find is that the distance is equal to 13. So I'll let you work through the details of that on your own. The point here is that we could use the fact that the distance squared is just as good as the distance in terms of trying to find the minimum distance from the point to the plane. Again, there's only one point here, and we know that it's got to be a minimum distance and not a maximum distance because I could move my point as far away as I like along the plane, because the plane of course extends infinitely. So I could move this point as far away as I want to get as large a distance as I want, but there's only one point that's the minimum distance away from the point 5, 7, 11. So once more with these problems, it involves a little bit of algebra and a little bit of geometrical thinking to figure out what exactly we're calculating.